did yesterday. So you who were here yesterday, you don't have to listen. This series of lectures is in honor of this person, Per-Olof Löwdin, who worked here for almost 50 years. He started in the 50s and worked here pretty much until he died, 2000. He's been a researcher that has introduced a lot of concepts in quantum chemistry that are of fundamental importance to how we do things. And I've just mentioned a few here, like natural orbitals, which is a way chemists today use to understand conceptually how reactions take place. We have Löwdin orthonormalization, which is a technique used in wave function calculations, etc., etc. He's also well known for having summer schools here in Uppsala during the 60s, 70s, and I believe early 80s. And also he started a department of quantum chemistry, not here in this building, but downtown. He started that in the 50s. Eventually the department became a department 58 years ago. I'm not that young, but actually he started up the first computer used for quantum chemical calculations just a month after I was born. That is the 26th of this, April, 1958. When he retired, a lot of his international colleagues got money together, and those money we are not now using to every second year call on people to come and give quantum chemical Per-Olof Löwdin lectures. And these lectures are, one day the lecturer will give a lecture that is addressing students, chemists, non-specialists. But today we're going to have the second part of it where we're going to talk science. Over the year there has been a number of different Löwdin lectures. Note, this is not a prize, this is an honor or a recognition. But here are some of the people, and those of you who are quantum chemists recognize probably many of the faces here. But I'm not here to talk about them, but to tell you who are the new Löwdin lecturers. So for 2017, Sharon Hames Schiffer is our Löwdin lecturer. Unfortunately, she can't be with us here today, and Thomas Schön has agreed to give a lecture on her behalf. And the second Löwdin lecture, 2018 years Löwdin lecture, is Markus Reiher, and we're very glad to have him here. I'm going to yield and give him the floor pretty soon, but let me just go through the schedule. So we did this yesterday, so we're here now. I'm doing the introduction, and then Markus is going to continue. We will have 2 coffee breaks, one at 10 o'clock, at 1 at 3 o'clock, and we're going to have a lunch break here from 12 o'clock to 1:30. The lecturers and I will go down to Rullan, and you're all welcome to join us there and have discussions together with the lecturers and the rest of the audience. And as I said, Sharon couldn't come yesterday. Sorry, Peter, for the cross in the face. Don't take it personally. Gave the lecture, and Thomas today is going to talk about machine learning, trends, and tools. So note that in your schedule. And with that, would just say thank you very much for coming, and let's enjoy the day. Oh, it didn't get that. Sorry. Is it there now? Yes.
Yeah, perfect. Okay, good morning everybody. Yeah, in my second talk, as you can see, I talk about the exploration of reaction mechanism. I chose the topic for two reasons. First of all, it's related to what I told you yesterday. And I understand that some of you didn't attend the talk yesterday, so there's some repetition here. I try to give it a twist so that it's not boring to those who have attended the talk yesterday. And the other reason is that it has a tiny bit on machine learning, and so it fits to the rest of the program. The point with respect to my talk yesterday is that yesterday I talked about fast quantum chemical methods. And actually I mentioned that fast methods where you sacrifice accuracy are fine as long as you know how wrong you are. But I didn't tell you yesterday how we actually assess how wrong we are. And I will talk about this today. But in a different context, because if you can do fast calculations, of course, you cannot only do interactive quantum mechanics, right? But you can also use this in automated screening approaches. And so this lecture will be a lot on automation of doing quantum chemical calculation on a massive scale. For the very same reason, like yesterday. So let me recall the reason. I told you yesterday that in chemistry, in order to really understand chemistry, you need to look at really complex reaction networks. And the reason is that what we often do in computational quantum chemistry is we study certain intermediates where usually our experimental colleagues tells us, well, this could be interesting and important, and then we figure out how these intermediates are connected through elementary reaction steps and so on, and we have transition states. And so what you basically do is you as a theoretician, you kind of confirm, usually, what the experimentalist already knows, right? And my favorite topic is catalysis. And when you think about catalysis, so what you would do is you calculate a catalytic cycle, and based on the energies that you get, you say, well, this is probably feasible, or there might be issues, right? But you wouldn't be predictive in terms of new catalytic processes, because what you look at is just only a tiny fraction of the catalytic network, because you won't be able to map it out manually. For instance, catalysts can decompose, right? And they deactivate, and then the catalysis is over. And usually these reactions you don't map out. But in order to be predictive, you need to be able to do that. And so I come back to my example from yesterday, where the catalyst is actually an enzyme. It's still the hydrogenase. And here you see the three classes of hydrogenases that I was mentioning yesterday, but I didn't show you the structure of the active site. So these are huge proteins, and in those proteins you have metal cofactors that are embedded in there, and they do the trick, like catalyzing this reaction. It's an equilibrium where protons and electrons are transformed into molecular hydrogen and back. And so there's these three classes. There's a mono-iron hydrogenase, the iron-iron hydrogenase, the nickel-iron hydrogenase. And look at these active site structures. Chemically, they are totally different, right? You see, the mono-iron hydrogenase, for a long time, it was believed that there was no metal at all involved in this. When I was a student, people thought that there's a hydrogenase without a metal cofactor. And then it turned out, no, there is one. It's a single iron atom, you see here, and then there was the first, this is an interesting story, there came the first X-ray structure, I think it was around 2005 of the system, and people thought that there was a carboxylate here coordinating the iron, which would be normal, right? You have the base of a carbon acid as a ligand. And of course people did quantum chemical calculations and were able to explain the whole catalytic cycle. Until the experimentalists found out it's not a carboxylate. It's an acyl ligand. You see this? There's no oxygen in here. So it's a very peculiar ligand here, this one. The quantum chemists did the calculations again, looked fine. I think it's an interesting piece. I mean, nobody does this, but it would be good to go back to figure out why in the first place people thought that this was actually a good mechanism, but usually people don't do this. So this is a very peculiar coordination environment for the iron atom. Here, this is a system you saw yesterday with the 6 iron atom here. There's a cubane cluster, an iron-sulfur cubane cluster. And that is the third class. It's a nickel-iron hydrogenase at just two metal centers. And yesterday I talked about oxygen inhibition. Today I talk a little bit about the mechanism itself. Again, we look at the iron-iron hydrogenase first. This is the active site model. This is a typical model that also Per Sigman would favor, where you take part of the protein framework, and then you fix certain atoms to mimic the constraints of the protein environment, right? And then you can do calculations. You have to, again, like yesterday, you need to inspect many structures, many different charge states. You need to make sure that the spin distribution in the broken symmetry calculation is reasonable. And so there are numerous calculations that you need to do. Once you're done with such a calculation, you can explain certain features in the mechanism. For instance, why you don't observe a bridging hydrogen species, which is in all biomimetic, or in most of the biomimetic model complexes. This is a species that is always observed, but not in the protein. That has to do with the fact that the protein exerts certain geometric constraints where kinetically this cannot be formed, and because that would be a thermodynamic sink. But this way you can explain what the system's actually doing, but then you would like to learn more about it and try to change things. Like, for instance, what do electric field effects do to the mechanism? Because people put these enzymes on electrodes in order to produce hydrogen, but of course that changes the mechanism. So you go back and you look at the mechanism again under the constraint that there are electric fields. And for instance, here you see in red the electric field at the iron atom, which is the active metal center in the iron-iron hydrogenase, actually in two enzymes taken from two different organisms, and so the proteins are slightly different, but still you see that the electric field that is present at the catalytic center is almost the same, and especially pointing in the same direction. And so you can start studying electric field effects on the mechanism, and that will change the mechanism, will change the transition states, will change the relative stability of the stable structures, and so on. And if you want to understand what happens to the enzyme on an electrode, you need to look into this. And so you need to go through all those calculations again. And then you might want to know what is the difference between these two hydrogenases. Yeah. So this is the iron-iron hydrogenase I was talking about. It's here on the right-hand side. And there was the mono-iron hydrogenase, where I told you there's a special acyl ligand. And when you look at it, right, you think, well, these are very different ligand environments. Not the way I wrote it, I depicted it here, but now you compare this one to the one in the middle, right? And so they are really different. But now I take a different view. I focus on the active iron center, and now when you look with the eye of a chemist to the ligand environment, so this is an octahedron, and the type of ligands is pretty much the same. Like here you see there are what a chemist would call sigma donors. You see strong ligands here, carbon monoxide. Here it's a cyanide. This is the ligand. This is a place where the H2 ligand comes in, or is formed, and then in the iron-iron hydrogenase you have a bridging carbonyl ligand, which is not unusual. But since there's only one iron atom in the other case, well, here comes the acyl ligand in, and right, it is locally it is of the same form. And when you look at as a chemist at these structures, they are totally different. But if you take this view, then suddenly they are similar, and that allows you to draw connections between the two mechanisms. And I was actually wondering whether such concepts can be extracted from machine learning. And I don't know whether you remember Anatol, but we talked about this some 6-7 years ago, right? This was on our list. It never happened, but it was on our list. Remember that? That you were visiting us, and then we showed you this example, and it immediately came to your mind. And that would be an interesting test case, I think, to figure out whether machine learning is actually able to extract chemical concepts in this way. Yeah, as yesterday, all of this was done manually, and I really think that this cannot be the future. Now, yesterday we talked about interactive quantum mechanics, where I can quickly tell the computer what I would actually like to explore in terms of structures. And now I take a little bit a different view, and you see a sketch here where I still want to map our reaction mechanism. And as an example, I take a map where, for instance, I want to go from the train station in Zurich, which is here, to our institute, which is over there. And so I try to figure out what the possible path is, and one you can see. But of course, there are many more paths to that place, and maybe I want to look at them too. But usually, this is what people do. You have some expectations on how to get from reactants to products, and you just work out the steps that match these expectations, right? But that is no risky adventure. It's mostly descriptive. Limited predictability, and it also limits surprises. So what we actually want to do is we want to map out the whole map, in this case of Zurich, or of a reaction network, of a complex reaction mechanism. And of course we can't do that manually. We want to do that fully automatically, locating intermediates, transition states automatically. Of course we want to steer it if possible, because there's a combinatorial explosion of structures if you just think about conformations, right? And I think there is no way to do this fully automatically. It runs automatically, but you need to interfere from time to time. It should be scalable. We want to have error estimation, because in the end we want to do kinetic modeling, so we need to know how good our energy data are. And so this is what we do. Unsupervised exploration. The interactivity, the steering of the whole process, we can do through the interactivity that I explained yesterday, through immersion-enhanced interactivity. We do extensive computing. We have a fully integrated automatism, so everything is in one framework, because we can't switch, or we don't want to switch between different computer programs. So we have first principle heuristics. I will tell you more about it in a minute, to figure out what reactive complexes are in order to explore the potential energy surface. We do kinetic modeling across molecularity and timescales, because we don't know what kind of network we map. So our kinetic modeling software or module needs to be as flexible as possible. And we need seamless uncertainty quantification. And that means that we assess the accuracy of our data already at the electronic structure level, then do this for all the contributions that we need for free energies, up to the point where we have uncertainties on rates and on concentration fluxes. The central data storage is our reaction network, which we can feed by interactive exploration or by automated exploration. Well, I will tell you more about this in a minute. And then we have automated benchmarking and refinement, because certain steps are just fast and not necessarily accurate. All I expect from the fast methods is that I see structures which are reasonable, because then I can refine them automatically. And once that is done, we can do kinetic modeling. Now, these automated exploration techniques, they are not new, of course. Many people have worked on this. I've listed a few papers here. We have actually recently written a feature article which is now online at Journal of Physical Chemistry A, if you're interested in this and want to read more about it. So I think most famous are these screening approaches for potential energy surfaces for a given potential energy surface by Maeda, Ono, and Morokuma. That basically map out all the stationary points for a given potential energy surface. Sometimes that's not really needed. So it's a very systematic method, but it has its limitations because of that. Then of course you know about the advanced sampling methods with reactive force field molecular dynamics, Born-Oppenheimer molecular dynamics, and so on. And then there are some approaches that were proposed in the past 5 years or so, which are heuristics driven. Most of it is based on molecular graphs, but molecular graphs limit you to a certain kind of chemistry, typically organic chemistry, with valence and bonding. If these are reasonable concepts, then that will work. If you go to inorganic chemistry, you will see that it will have problems. And that is why we looked into reactivity descriptors. It's also heuristics, but based on first principles. So we calculate the electronic wave function, and we extract our descriptors from there. And that works for any kind of molecule, of course. We want to invest cheap computer time, and what comes in handy is our work on semi-empirical methods. I talked about this a little bit yesterday. We also worked on transition state search engines in order to have those transition state searches as stable as possible, because everything runs automatically. If, out of 10 searches, 9 fail, then that wouldn't really work. Stable orbital optimization is also an issue, because if you do so many calculations, it's pretty much the same problem that you have in ab initio molecular dynamics. You can't check whether the electronic solution that you get, the set of orbitals, is actually reasonable, because there are usually more than one solution to a problem. You have local minima, and you need to make sure that you actually get the orbitals to the lowest energy. And so we have come up with fast and efficient, stable algorithms that probe this. In the end, you have a big data problem, which basically means that there is no way that you can manually inspect the data. So you have to find a way to do the evaluation of all the data automatically. This is done in, so I told you yesterday already, our software project is called SIGN, and SIGN consists of different modules. And the module for the automated exploration is called Chemoton. Chemoton is a name that was coined by a Hungarian chemist in the 70s, referring to biochemical networks. And that's where we took the name from. You see here a network. That is actually a network that you would see on the screen. Of course, this doesn't talk to you. It does only talk to, it's raw data. It talks only to the person who really is working with this. But let me guide you how to step by step through this so that you can understand what's actually encoded in here. And I do this at an example, and that's the foremost reaction. This is a condensation reaction which starts from formaldehyde and creates complex organic molecules, for instance sugars, and for that reason it was considered as an important reaction in prebiotic chemistry. So what our algorithm would do is you draw your structure, and then the computer turns it into a Smiles code and then into a three-dimensional structure and automatically optimizes it. And this is what you then get. And on the screen you would see a dot, right? This green dot. Now what the computer program would do next is it generates automatically all conformations. Because it could be that you need to look at different conformations and you don't know a priori what are the important ones. So you get, for one compound, you get different conformations. These are given here in blue. And of course, depending on the size of the molecules, there can be really very many. Okay, and so we have some criteria to cut this, depending on energy, which relates somehow to temperature. And so those high energy conformations we throw away, just to keep the whole exploration feasible. And then the next step is that the computer takes these conformations and creates reactive complexes, right? And they are given here in yellow. These reactive complexes basically are a way to push two atoms of two reactants on top of one another, right? And we do this screening for orientational degrees of freedom. So it's not just one calculation, there are several of them. And of course, this also creates a combinatorial explosion of structures. In order to tame that, what we do is we exploit these heuristics concepts. And so, for instance, we do use descriptors from conceptual density functional theory. Right? So we calculate an electronic wave function and then we evaluate the descriptors. The simplest way to look at this is, for instance, you consider partial charges, you compute the partial charges quantum chemically, and then you pair up only those atoms which have opposite partial charges. Right? That's a simple way to do that, but you can do that, of course, in a much more sophisticated way. Yeah, and then we relax the structure. So we have created a high energy structure on the potential energy surface, and now we optimize it looking for new reaction channels. Right? And these structures, these sequences of structures are given here in orange, and you eventually end up in a valley where the forces again vanish. Now you need to analyze automatically, of course, what you got. Right? And the first thing you do is, rather than looking at the result here, you actually first go for a search of a transition state for this path. Right? You pick one of these structures here, which is a high energy structure. You optimize the transition state, that is the one here in red, and then you do an intrinsic reaction path calculation to figure out what kind of valleys are actually connected. So what are the reactants and the products? They are given here in violet, and then the computer, of course, needs to figure out how many molecules are actually now represented in your set of coordinates. So it decomposes based on bond orders computed again from the electronic wave function. It decomposes the molecular structure here into individual molecules, and these are now given here in gray. The next step you need to do is, because you cannot afford any redundancy in the network, you need to figure out whether you have seen these structures before. And so that's what the computer does next. And you see, in this case, this gray dot was identified as that conformer, and this one as that. This is a new compound. It becomes a green dot, and then again we create conformations of that green dot. And this is how we proceed through the network, right? And of course, then what you get is you get very many reaction steps that actually do the same chemical transformation from compound A plus B to C. because you have the different conformers and the different orientations in the transition state and so on. And so what is done then is it is automatically processed into such a reaction of compounds A and B to C. Let me give you an example for the foremost reaction. These are DFT calculations in a double zeta basis. Actually, we carried out 150,000 calculations automatically, figured out 1,000 unique molecular configurations, 10,000 transition states. Everything was stored in a MongoDB database, and then it was analyzed. And this is a result. So this is a graph of the reaction network that we found, the most complex reaction network for the system that was mapped out so far. You see, these are all in color. These are all individual compounds. The color code is that the greener it is, the more carbon atoms it has. And in violet, you see trioses, in orange, tetroses. And in blue, these are the starting materials, like that one there. Okay, so if you have all the information there, and of course you can extract detailed chemical information from here. For instance, you could ask the question, okay, what are the pathways that actually provide me with sugar molecules, right? And then out of the scheme that you have seen before, we can extract this information. And you see here now, I can draw circles which are large enough so that you can see the individual molecules. So all this information we can now extract from a reaction network. By the way, it took 2 weeks to generate that. Okay, just 2 weeks. Okay, and that is related to what I talked about yesterday, to the fact that you can do these calculations so that full interactivity becomes possible, and that's the second block of repetition of 3 slides that you have, 4 slides actually, that you have seen yesterday. And that's when I talked about real-time quantum chemistry, where the calculations are so fast that the information flow is such that you need to come up with different ideas to perceive the information, such as force feed, haptic pointer devices, to experiences, forces, and so on. And already yesterday I told you that we can use this for reactivity studies. And of course, the interactive exploration and the automated exploration, they all write into the same database. Okay. You saw this example of molecular propensity yesterday, where you can, because the calculations are fast, you can run calculations in parallel that can tell you about instances that you haven't thought of, which can be important for the network. For instance, that the system has a tendency to be reduced or to change spin state, as in this case. And this is a case of, this was the second case that I discussed yesterday, where we have a protonation reaction that is facilitated by electron transfer. So you see, you get from the calculations, you get a hint of proton-coupled electron transfer. And yesterday I didn't point to the exploration coordinate here, and I would like to do this now. You see it runs from 0 to 5, and that is in seconds. Okay, to figure this out takes seconds. And I told you yesterday that the surface is bumpy because this is a manual exploration. What I didn't tell you yesterday is what we do with the bumpy surface. And since this is now important for the mechanism exploration, I do it now. So we have this bumpy path, and then we have a module that uses B-splines to get a smooth path, and actually we use then the B-spline representation, so the representation as a curve, to optimize the transition state. Our transition state optimization does not change individual structures, it changes the parameters in the curve to eventually find the minimum energy path. Okay, and that is the data that we then store into the network. It's not the explored data, which is noisy in a sense because we have a manual exploration, but it is this data that then goes into the network. Okay. Now, we have modules that allow us to map out complex reaction mechanisms, and so the next question is, can we do kinetic modeling? If we can do kinetic modeling, that is great, but you know that all rates depend on the energy differences through an exponential. So if you have a tiny error in an energy, it will be disastrous for a chemical rate constant. Yeah? And so we need to worry about accuracy issues, and this is what I would like to discuss next. What you have seen are all DFT calculations, and those of you who have done such calculations know that they have unpredictable accuracies, which is kind of a problem. Right? Often it works, sometimes it does not, but you need to know when it does not. Right? The problem with DFT, in my view, is that you see all large mean absolute errors, even for the benchmark sets, which is for kinetic predictions really a huge problem. So if you have such a large mean absolute error, what about the transferability? I mean, that is the benchmark set, right? And you're not really good at the benchmark set. And that's not acceptable for predictive work. Now, I don't believe that DFT can be really pushed to accuracy limits. There will be limits in accuracy which are of a kind that kinetic modeling will always be problematic, by contrast to wave function based methods. But at least I need to know what the error could be. So the first step that we took is we thought about, can we actually know how wrong DFT could be? Can I know for a specific case, not on average? An average statement doesn't help me. I need to know for an elementary step in my network how good the DFT results actually are. And there's an interesting paper, I really like this a lot, from Nørskov, Cessna, Jacobson in PhysRef Letters 2005. And that builds on Cessna's work on sloppy physical models, where it's possible to map the real error for some data points that you have to a sampling error of DFT functionals. And that can be done in an exact way for all the linear parameters in your model, for all linear parameters in the functional. Of course, there are non-linear parameters. For those, it won't work. Now, this idea was then exploited to give and gave rise to functions which you might have seen before. They are more popular in the solid state community than they are in the molecular physics community. Functions like beef van der Waals or M-beef. The problem here is that the mean absolute deviation is still very large, 60 kilojoules per mole, then 34 kilojoules per mole. There are updates where this was further reduced, but not up to the point where you can really do kinetic modeling reliably. And so we thought, well, okay, the idea is nice, but let's go for system-focused parametrization, right? So this would be then DFT in a truly semi-empirical way, because I get a functional for a specific system, but actually I wouldn't care if I know how wrong this is or how good it is. Okay, so we have a specific DFT parameterization for a tailored benchmark set. What we chose was a range-separated hybrid functional, because those functionals are in molecular physics the best which are around. So we thought it would be good to start with this, and also Jacobson, Nørskov, and their groups, they haven't looked into hybrid functionals at that time. And that this idea of Cessna actually allows us to get error estimates for our data. So the functional that we use is LCPBE0, and we gave it a star here because for our specific problem, we optimized all the nonlinear parameters. Remember that only the linear parameters can be used for the error estimation. And here you see reaction energies. That is for the Formose reaction that we have discussed before. The zero line, these are coupled cluster data, and then you see the deviation of DFT data. In black, that is our functional attached with the error bars, and in color, you see you see popular functionals like P3lib, PP86, PBE, PB0. And now what you would expect from a method of error, from an error estimation method that works, is that the zero line is always covered by the error bars. And you see that it's not always the case. So what you see here is a limitation of the physical model. So the functional is simply not flexible enough for the training set to make sure that the zero line is always within the error bars. What you can also see is that it is not true what people usually or often think, that if you consider a sequence of functional, you pretty much know something about your accuracy. Right? That is not true. For instance, let me give you this example. Here you see a huge spread of standard functionals, whereas the error is actually much smaller. And you see other cases where it's the opposite. Yep. Yeah, it's 2 sigma. Exactly. Yeah. But we were not satisfied with the accuracy. So this is now, so that was the training set. Now you see the test set. Pretty much, you see more reaction energies, but those were not used for training, and you get basically the same picture. But we were not really happy with the accuracy. And we were not happy with another fact, because we have a rolling network exploration. So we generate new data and new data and new data. If we want to feed in the new data into this error estimation procedure, we need to refit always the functional, redo all the calculations. It's just too expensive. So we need to do this in a different way, and this is where machine learning comes in. Right? Because machine learning gives you techniques, more than one, that you can use in order to assess how good your estimates are, because you do have always confidence intervals, and actually we used for this Gaussian processes for various reasons, but I'm sure you can also use deep neural networks, but we haven't tried this. I guess we will hear more about Gaussian processes during the day, and since I am not the expert, rather the experts are here in the audience, I leave it to the experts to explain how Gaussian processes actually work. What we did is we came up with an algorithm, and I also cannot explain this because all these quantities are rigorously defined in that paper, and it would take too long for me to explain all the detailed quantities. But the point is the following. So we have, on a potential energy surface, certain stationary points. Those are calculated with a DFT functional. And for these points, I also do an accurate reference calculation. For instance, a couple cluster calculation. So now I know how wrong certain energy differences are, because I can directly compare the DFT result to a couple cluster result. What I now want to do is I want to expand, so explore more of the potential energy surface and also different potential energy surfaces. And so I need a descriptor that tells me how far I have moved from the data set that I have already generated, up to the point where I automatically need a new benchmark result, and then I do a new couple cluster calculation. I add it to the data that I already have, and I do what we call backtracking to change everything which I already had, so that the whole thing is again consistent. Right? And then there are certain stationary points which are similar to the points where I have the benchmark data, and then through the machine learning approach, I know how accurate the DFT is. Okay, that is basically the idea. And that can be done with Gaussian processes or with other machine learning techniques. Okay, so this is now a way to assess the quality of the data and also to improve on it. I should also say what we exploit from the machine learning approach is actually the confidence intervals. We don't create a machine learning model itself, right? And we can be very conservative here. So we can run more reference calculations than needed. So that is why I think that we are rather insensitive to weaknesses in the data, in the descriptor that tells us how similar a structure is compared to some other structure. And then the next step is, of course, we can do kinetic modeling. And there are commercial products available for this, and I guess the most well-known program is ChemKin. And there are also programs you can buy this and do kinetic modeling. There are certain solvers which are specific, for instance, for non-equilibrium thermodynamics that you can find in reactions with highly reactive species. And one of these is the MESMA program that was written by Dave Glowacki, the same Dave Glowacki who you have heard about yesterday, who set up this virtual reality environment. In our case, we need to cope with multiple timescales, and we don't know what kind of molecularity our reaction steps have. And the kinetic solver needs to be able to cope with anything that is found, right? And it also is supposed to have a seamless uncertainty quantification. So we have the uncertainty in the electronic structure data, and we can play similar tricks for all the contributions to the free energies, which we eventually need for the kinetic modeling, because it's the free energy differences that enter, of course, the rate expressions. And we need to know how accurate the data actually is. And so that's why we came up with a variant of computational singular perturbation, which is an efficient way to do first a timescale separation. So we have an automatic scheme that allows us to isolate the fast from the slow processes. Then we equilibrate the fast processes first, and then we do a slow step, and then we go back to the fast processes. Okay, and then we can do the uncertainty propagation, starting from first principles, and also connect this directly to the exploration. So we can use the kinetic modeling to steer the exploration, which allows us to have a very sophisticated way to cut out passes that are just under certain reaction conditions not accessible. because barriers are too high. Okay, this is an example, an early example. It's a section out of the Formose network. You see there are just 6 species here. And we have, of course, calculated the reaction, the barrier heights, the transition states, and know the rate constants. And this is basically the algorithm that we use in our kinetic modeling, this variant of computational singular perturbation, where you see this is all the elementary reaction steps can be combined in this vector representation, where you have here the rate of change of your concentration, and this is the time derivative of the species concentration, and then there's a stoichiometry matrix and what is called the reaction pair vector. From this you can calculate a Jacobian. That one can be diagonalized, and from the eigenvalues you can learn about the time separation, and that's what we do. And then we equilibrate the fast steps, and then we make a slow step. And this is then the result. Actually, we picked the Formose reaction because we thought that DFT will work fine there, because we know that it has trouble for transition metal systems. So that's why we went first for an organic reaction. And what you get as a direct result is shown here in red. And so 1, 2, 3, 4, 5, 6 are the 6 species that you have seen here, right, from the Formose network. And here in black, this is the spread that is due to the uncertainty. So we were very much surprised that DFT is still so bad for organic chemistry that the spread is huge. I mean, the qualitative behavior is more or less the same, right? But in quantitative terms, there are huge differences because of the errors that we still have on the energies. We have elaborated on this, and it will become a module in our SIGN project. It's called kinetics. It's described in this paper. We have submitted it to JCTC, and the revised version is still under review, but you can have a look at the archive. Since March, it's on the archive. Okay, next and final step. Well, if this works, we need to do reference calculations. And I told you we do coupled cluster calculations. But coupled cluster is only good if your electronic structure is single reference. How do you know? Right? So if you can figure out that your structure is single reference, do a coupled cluster calculation. It's the best you can do in a proper basis and so on. And we came up with a multi-configurational diagnostic to do this. Of course, within coupled cluster theory, there are also diagnostics, but you might want to criticize that. I mean, they usually work, but there's some criticism because it's extracted, it's an information on multi-configurational character extracted from a single reference wave function, because you only have a single reference wave function, meaning a single Hartree-Fock determinant. But what if you have a multi-configurational case? So we have a multi-configurational diagnostic which is actually based on a DMRG calculation. And so DMRG, I mentioned this yesterday only briefly, is actually our solution to the problem, because it produces a very general wave function. It produces a CAS-SCF wave function. And so that's a suitable qualitative wave function for any kind of structure that you might encounter in a reaction mechanism. The problem is it's quantitatively not correct, because you need to add perturbation theory on top of it. There are more issues to this, because for a long time DMRG was believed to work only for quasi-linear systems. So it works excellent for one-dimensional spin chains, but molecules are not one-dimensional spin chains. They have always a three-dimensional structure. And the Hamiltonian that describes our molecules, you have seen the Hamiltonian yesterday, in the end couples always 4 orbitals through the electron-electron interaction. And for the spin chains, you can usually work with the nearest neighbor Hamiltonian, for which DMRG works fine. But it turns out that in practice, DMRG converges, although it should have problems. So that's why DMRG turned out in the last 10 years as a reference method, which I think not many people saw coming, because very many people thought that this is some esoteric way of doing calculations which will lead to nothing. But actually DMRG is now the way to do CAS-SCF calculations for huge active spaces. And this is actually what we need. We have our own program. It's now also a part of the SIGN package. It's called QC Markus. What DMRG does actually is you see an electronic wave function expanded in terms of configurations. You have CI configuration interaction coefficients, expansion coefficients, and these coefficients are actually decomposed in the sequence of matrices, and the entries in the matrices are optimized. And so this is a very special way of writing the wave function, and it's called the matrix product state representation, and you can adopt a very similar representation for any operator that you might be interested in, for instance for the energy. And so this is what our program does. We do have, I should say that we have full spin symmetry adaptation, which is important because otherwise you can't trust the energies. But it's a CAS-SCF approach, right? And some of you know that we have worked on automated orbital selections for an active space. And that was for two reasons. We just need this because we need to drive the DMRG calculations in an automated way. If there needs to be a user who picks the active space manually, right, then the automatism is broken. So we can't have that. And the second reason actually is I never liked the fact that you should have a set of rules which tells you what kind of orbitals should be in the active space, right? I mean, you have a very sophisticated quantum mechanical methods, and then there's a set of rules which requires an expert. And you know, in science we can't have wizards who really know how things work. We need to come up with concepts that can do that automatically, and that's why we worked on this. So the way we do this, we don't use natural orbital occupation numbers for the simple reason that they do not give you enough information to really pick the orbitals. If you have a really complicated correlated system, then you will see that natural occupation numbers are very similar, and then you don't know which orbital to pick and which not to pick for the active space. And so instead we use entanglement measures. These are calculated from orbital entropies, and actually we need what is called a single orbital entropy and a two orbital entropy. And for the single orbital entropy we calculate a reduced density matrix. And now this is a very special reduced density matrix, not of the standard kind that you know from in quantum chemistry. So it's not a 2-body or 3-body or 4-body reduced density matrix. It's a one orbital reduced density matrix, which means it's grand canonical because it considers 4 states of an orbital which are unoccupied, spin up, spin down, doubly occupied. So the reduced density matrix for a single orbital is always of dimension 4 by 4. You diagonalize it, you get eigenvalues, and these are these W's here in a Shannon-like entropy expression, and you sum over all of them and you get the single orbital entropy. You can do the same for the two orbital entropy. Now you have 4 plus 4 states, so quantum mechanically 4 times 4 gives you 16. The dimension of the matrix is 16, and you have 16 eigenvalues. And this defines then, when you sum over this in the Shannon type information entropy expression, you get the two orbital entropy. But it contains a single orbital entropy which you would like to take out of it, and that then defines the mutual information. So we work actually with the single orbital entropy and the mutual information. The single orbital entropy, the nice thing is defined for a single orbital but extracted from a full-fledged electronic wave function. Whereas the mutual information is defined for a pair of orbitals. And now the numerical values of these quantities are really not important, and you can depict the results in these entanglement diagrams where the red circles measure the size of the red circles measures the single orbital entropy, whereas the connecting lines, the thickness of the connecting lines measures the mutual information. For instance, you see that 6 and 7, these orbitals are strongly entangled, and that's where you find a huge single orbital entropy and a huge mutual information. So this is for the case dioxygen in the singlet delta state. And in this state, there are 2 molecular orbital diagrams which contribute, namely this one and that one. And you see there are these degenerate orbitals, 6 and 7, which you can doubly occupy here or there. And that's a typical multi-configurational case, right? And these entanglement measures figure out what are the entangled orbitals, those orbitals that make it a multi-configurational case. And that's the reason why you can use the information encoded in these diagrams to extract information on what orbitals are to be chosen for the active space. We have turned this into an algorithm, and I will not tell you anything about the details. This is just a picture to show you that there is an algorithm. It consists of 3 steps. We do first a partially converged DMRG calculation. The nice thing is with DMRG, you can look at really large active spaces, and you can do a quick and dirty calculation where the energy is crap, but the qualitative nature of the wave function is actually pretty good. If it is not, you would understand in after you go through all the steps, and then you could go back and do a better calculation and repeat the scheme if it would fail you, which it never did in all the cases where we looked at. So you use that information to identify the important orbitals. Those are the ones to pick for the active space, and then you converge a decent calculation. This is an algorithm that we have connected to our QC Markus DMRG program, and it is a graphical user interface called AutoCAS. You can download it from our webpage, and it is connected to the Open Mulcast program, which is where Uppsala is a major hub. Let me show you one result of this scheme. Here you see what Chris Kramer called the Cu2022 plus torture track. You see this is a core which is essential in certain metalloenzymes. We have two copper centers and they are bridged by two oxygen atoms. This is a bis-muoxo compound. It is this one. But in fact, you can these two oxygen atoms can get closer and form a bond, and then you would have a peroxo structure. And you see the peroxo structure here on the right. And of course, that is important for the chemistry of a system. And so Chris Kramer in 2006 looked at this with various wave function methods, also with KSSF, and he found that KSSF fails miserably. That is here, this red curve. The reference is a completely renormalized coupled cluster calculations from Piotr Pirzuch, which is this result over here, and you see the difference is enormous. The reason for that is that the active space in a standard KSSF calculation is just too small. But since DMRG can do a better job here, we choose basically the full valence space. You have 48 electrons in 36 orbitals, and we do a quick and dirty DMRG calculation, and you see the energy is all over the place. It's totally useless. But from that, the wave function is okay, and from that information we pick the orbitals, and then we do a decent calculation. The decent calculation requires 32 electrons in 28 orbitals, and we get this black line over here, and you see that the agreement is very good. It's not perfect. It must not be perfect because we still lack dynamical correlation. If you add dynamical correlation on top of it, you get the coupled cluster data. This brings me to my conclusions. I've shown you now all the elements that we have developed for automated reaction mechanism exploration. We can do these massive automated surges. We can combine that with interactive real-time quantum chemistry to steer the surge if necessary. I mean, if you realize that the computer is doing really something crazy, you can just stop it. We can do kinetic modeling for different time scales and beyond first-order kinetics. We have Bayesian error estimation for DFT and semi-empirical results, and we have worked on rigorous automatized benchmarking, where we would use for single reference calculations explicitly correlated coupled cluster methods, and for the multi-configurational cases, DMRG plus multi-reference perturbation theory. Yeah, I told you already yesterday, some of these modules have already been released. We try to release everything within the next 12 months, and you can have a look at this webpage. I'm grateful to all the people in my group who did the work. You see a most recent picture over here. Support was, as yesterday, from ETH Zurich, Swiss National Science Foundation, but for these topics also from the German Fonds der Chemischen Industrie and from the Austrian National Science Foundation. Thank you very much for your kind attention.
Yes.
No. Of course, this is what we want to do. This is what we are right now working on. You can do different things. So our idea is you would first map out the generic network with a basic structure, no substituents. Would be fast, and you have a generic structure. Then, since you have all the structure, you can introduce substituents wherever you want. You can exchange metals. And then the system can automatically relax this network and also search for new pathways. This is what we do. So I think this is crucial for design. Yes. So what we have used in that paper was the SOAP descriptor developed by Gabor Czarny. You could also think about the Coulomb matrix. What we actually do now is we try to have our own descriptor, which also uses electronic structure information, like what Heather has done already. Because I think pure geometric information is not sufficient. I don't know. It's simple to understand. I mean, say you have a reaction. These are the reactants, these are the products. In between, there's a transition state. you know that you can have similar accuracy for the two valleys, but for sure it has not the same accuracy at the transition state, although the transition state is similar to one of the, or actually similar to the reactants and similar to the product. Then the reactants and products are, it can't be that it's only geometric information. So we are working on this right now. And that I don't understand. No. What we do now is we compare the structures in the stable valleys. And what I'm saying is, if you would now compare to transition states, you must not draw a conclusion there, because the error is not necessarily the same, for the simple reason that for the reactants and products you usually have closed shell structures, for instance, but at the transition state you reach the multi-configurational regime. So the electronic structure changes, and that's why I think you need to have the electronic structure in there. What you could do, I think, which we haven't done that either, is you could treat different classes of structures. I think you could, you put the transition states in one class and the stable intermediates in one class. It probably would work too. But since our paper is from this year, we are still trying to figure out what the best option is. Going back to the system. So I also have a PhD student who works on automated QMM models. Once I've done that, I go back to the system. I usually choose an explicit example to develop the methods for. And so we have an actual enzyme, but that is from a collaborating group at EMPA in close to Zurich. And so we do the development for them, because they also have a lot of kinetic data, and we can directly compare and see how good we are. And so once this is done, then we can go to these enzymes which are so important and so interesting, like hydrogenase, nitrogenase. Yeah. Thank you.